Hello, math analysis students. In this video, we are going to learn about how to graph logarithmic functions. Now, it's important to note that logarithmic functions and exponential functions are very closely related to each other. They are inverses of each other. If we were to look at a graph of a basic exponential function, like we talked about in the last video, you see it has this curve here, it goes up, and it approaches a horizontal asymptote. For our logarithmic functions, we actually have a vertical asymptote that it's approaching, and over here, these values as we go to the right, they're going to keep increasing, but they're increasing slowly. Our exponential functions were increasing rapidly. Logarithmic functions are increasing slowly. They don't have an asymptote that they're approaching, but they're just getting bigger pretty slowly. And these two graphs, being inverses, that means they are symmetric over the line y equals x. So they are mirror images of each other. With our exponential functions, we have a key point right here of 0, 1, and a horizontal asymptote. With our logarithmic functions, we have a key point right here at 1, 0, and we have a vertical asymptote. So those are our big ideas. You'll also see how the domain and range are related to each other. Okay. So, our basic parent logarithmic function, we've got two types of functions we can have, two different bases. This one we have y equals log of x, and then we have y equals this ln of x, stands for the natural log. Again, our basic function for a log looks like this. Our base, b, for a common log, that's where we just use the log, that is base 10. And then we have the natural log, which is using base e. And base e is Euler's number, and it's a number that's roughly 2.718, I think. And when you see this abbreviated, log is log, and the natural log is ln. Okay, the key point for our basic logarithmic function is 1, 0. Now obviously that is very similar to 0, 1 that we had for our exponential functions, but if it helps, you can think about 1, 0, it looks like the L, the O, and the word log. For the logarithmic functions, we have an asymptote that's a vertical line, and a vertical line has an equation x equals. And for our domain and range, you'll see they look kind of similar to our exponential functions. But on exponential, we had a domain that was all real numbers, and our range was everything on one side of the asymptote, the horizontal asymptote. For our logarithmic functions, our range is all real numbers, and our domain is everything that's on one side of our vertical asymptote. So when we start transforming, we still have the same values that we were looking at before with exponentials a and h and k that have an impact. A has to do with the steepness, and also if there is a flip, if we have a reflection. H is our horizontal shift. K is our vertical shift. All of these transformations are based off of our parent function with a key point of 1, 0, and an asymptote at x equals 0. Our bases here are the same. We could have the common log of base 10 or the natural log of base e. Our key point, once we're shifting from this point 1, 0. So this time our x's are being shifted over. So that's h plus 1 for our x coordinate, k for our y coordinate. And I'm going to go ahead and talk about our asymptote for just a moment. We have a vertical asymptote at x equals h. Now our domain here is everything from that vertical asymptote of h on over. And our range is all real numbers from negative infinity up to positive. So these are our key values that we're going to be using when we graph some logarithmic functions. Now with our exponential functions, we could plug in values of x and get out values of y. With our logs, We have not yet learned how to evaluate those, and there's a lot of things we're not going to be able to evaluate without a calculator, so I will be showing later how to use Desmos to evaluate these. Our steps for graphing logarithmic functions are exactly the same steps that we have for graphing exponential functions. Identify h and k, identify the base b, find the key characteristics, your key point and your asymptote, plot those key characteristics, and then make a table and graph. So let's go ahead and graph this function. F of x equals log of quantity x minus 3 plus 2. All right, identify our a, h, and k. A is just 1, h is 3, k is 2. Our base here, since we don't have the letter ln, that's a common log, which is base 10. So common log of base is 10. Let's find the key characteristics. Our key point is h plus 1 k. So h plus 1 is 4, and k is 2. And our vertical asymptote, x equals h, so that's x equals 3. We could plot these points, our key point of 1, 2, 3, 4, 1, 2, and our vertical asymptote at x equals 3. There will be nothing on this side of the graph. When we make a table and graph, we would not be able to really evaluate things unless we use Desmos. So I'm going to go over to Desmos right now. I'm just going to plug in a couple of numbers and show you what happens. On Desmos, to evaluate logs, we need to go to our Functions tab, and then it's over here under Miscellaneous. And you'll see down here we have the ln for natural log, we have log for common log, base 10, and then we also have logs with a different base. We will have an example of that later that we will use. So if we wanted to evaluate the log of, I put in that function right here, x minus 3 plus 2, then you'll see what's happening with this. And I'm going to go check out the table for a moment. And you'll see that we have all these values over here that are undefined until we get to bigger, more positive values. So all of these are undefined, which means we have nothing going on this side of the graph. But if we put in our key point of 4, then so if we put in a value of 4, we get out a value of 2. If we put in a value of 5, then we will get out a value of 2.301. If we put in a value of 6, we get bigger values. We could put 7, and you see that our numbers are increasing here, but they're increasing pretty slowly. So when we go back and graph our function, and we would plot these points, we had values of 4, 2, and we had a value of 5, 2.3, 6, 2.5. We would graph, it's getting bigger here, and here it's approaching our asymptote. Okay. We're going to do a couple of more examples. For this one, we have the log base 2 of the quantity x plus 1. Our base here, this is not base of 10. You see that this 2 right here, that means that is our base of 2. So if we were going to enter that into our calculator, we need to use the appropriate log on there. We'll demonstrate that in Desmos in a moment. Our h value is -1, and our k value, there's nothing back here, so our k value is 0. Our key point here would be h plus 1, which would give us 0, and k, which is 0. Our asymptote, x equals h, x equals -1. Our domain is everything from this vertical asymptote on over, so from -1 to infinity. And our range, everything from -infinity to positive infinity. Key point is 0, 0. Our asymptote is at x equals -1. And it would be everything on the right-hand side of it. We know that our values are going to get closer and closer to this asymptote. And then to get these other values, let's go over and check out decimals for just a moment. So here, this is where, since we have a base that is not e, base of natural logs, or 10 common logs, we would want to use this one right here that has log, and we would want to enter the base. This has a log of base 2, so we would enter that there. And then we would put in our x plus 1. And there we go. So within our function, we could get some values for this. If we go to our table, then we see that -2 is undefined, -1 is undefined, 0, 0, 1, 1, and 2, 1.58. So when we would get those points back over here, 0, 0, which was our key point, 1, 1, and 2, 1.58. These numbers will keep getting bigger, but they're getting bigger slowly, so you get some nice curve. Keeps going. Our next example, y equals ln, or the natural log of x plus 4 minus 1. Our base here, this is a natural log, so our base is e. Our h value is -4. Our k value is -1. Our key point, h plus 1, which is -3, and k, which is -1. Our asymptote is x equals h, so x equals -4. Our domain is everything from this asymptote on, from -4 to infinity. Our range goes from -infinity to positive infinity. We plot our key point at -3, -1, and our asymptote is at x equals -4. If we wanted to get those other values, we go over to Desmos. In Desmos, we would go to our functions, go to the ln, or natural log, x plus 4 minus 1. And we can see that that matches with our key point of -3, -1. It's there. We can get our table of values. And to see these, we're going to go back over and just plot some of those values right now. We have the -4 does not exist, -3, -1, -2, it was -0.31, -1, this is here. So we're closer and closer to our asymptote, and then here they're rising slowly. Our last example, we have y equals -2 times the natural log of x. So whenever we say a negative out front, we know that that flips. Our basic function, our basic logarithmic function looks like this. Then a flip is going to look like this. Our h and k values here, we don't have any extra horizontal and vertical shift going on, so h is 0, k is 0. Our base set, since it's natural log, our base is e. Our key point, 1, 0. And our asymptote, x equals h. Our domain, everything from our asymptote, or our h value, on over, and our range from -infinity to positive infinity. We graph our key point, 1, 0. Our asymptote of x equals 0. And then to get those other values, to know how quickly it's increasing, we would need to use our calculator again. At 0 does not exist. 1, 0. At 2, it's -1.4. And at 3, it's -2.2. And so our graph is getting closer to the asymptote, and here we're getting a nice curve. We will practice doing some more problems with graphing logarithmic functions in class next time. See you then.